Hi,
Oh, hi.
Yvonne, I'm here.
Oh, hi. Great to see you. So, Professor Alexander Ling, Alex is Director of Quantum Engineering Program at National University of Singapore, also a colleague and friend of us. And his title is The Assessment of the Suitability of Satellite Quantum Communications under Realistic and Finite-Sized Statistics. Thank you, Alex.
Thank you very much for the kind invitation. What I want to talk about in my talk is about how to build a global network for quantum key distribution. And I think, Arthur, who preceded me, must have talked a little bit about what quantum key distribution is. And we know that there are people around the world trying to build that on the ground using optical fibers or using free space links. But what I'm talking about today is the challenge of extending such networks to a global scale using satellites. And in particular, I'm talking about satellites that are shoebox-sized satellites, as you can see in this picture over here, which is a shoebox-sized satellite they call a CubeSat that's being launched out of the International Space Station. So the title of my talk is really, about what are the realistic rates that we can expect in quantum key distribution when we are using such small satellites that are constrained in size, weight, and power, right? Because once you begin to take these considerations into account, you very quickly realize that your transmitter is not perfect. It is small. It's typically about 10 centimeters in diameter. Your receiver maybe is half a meter in size, but it's 500 kilometers away. So you need to begin to start to take into account the budget, the link budget, right, when you have such a system. And this is some recent results that my research team have put together with some collaborators from around the world. And I'd like to share some of these results with you uh, in today's talk. So just to recap very quickly, the challenge of quantum key distribution, right, is about helping to distribute a symmetric key to two people who want to communicate, right? And the most common way we're doing symmetric encryption today is using AES with 256-bit key size. And we have lots of classical algorithms with which we can distribute these keys secretly. But we think that in the post-quantum world, when quantum computers become ubiquitous and become powerful, this classical algorithms for distributing the secret key may not be secure. So we look for what we call quantum safe techniques to do that. And what's a quantum safe technique? Well, it simply means a way in which you can distribute a secret key, which is robust against a computational attack or robust against the presence of a quantum computer. So you can think of, a secret courier, in a van that goes from place to place distributing the secret key. Or you can even think of, using more old school techniques like carrier pigeons or post-quantum crypto algorithms. But of course, we also know that by exchanging quantum signals between the two people who want to communicate, you can convert those quantum signals into a secret key, right? And this technique in general is called quantum key distribution. And we have actually a family of quantum key distribution protocols, right? You can take single photons and transmit them. You can take lasers, attenuate the power until they approximate that of a single photon. And then you play around with the photon statistics. So you can use decoy state methods, or you can use the technique of entanglement, which Arthur Eckert actually invented about 30 years ago. And using this variety of QKD protocols, people around the world are actually building these networks. China has the largest QKD network in the world. Some of the links that span, the distance between Beijing and Shanghai, which is over 1,000 kilometers long. But on a smaller scale, lots of countries are also building the same things. For example, in the US, between a data center and trading houses in New York, such a system is being built. In South Korea, they're building networks to test out how QKD works to secure the backbone of the 5G network. In Singapore, we are starting to look into doing similar exercises as well under the quantum engineering program. We know that the fiber networks in Singapore are actually very stable. We can distribute entanglement through those fiber networks very reliably, right? And we want to start, putting appliances into this network to test out the use cases. But all of these techniques that I'm showing you here on this slide are relatively short range. They often rely on optical fiber. And optical fiber is lossy, right? You can send quantum signals over an optical fiber and maybe reach 50 kilometers or so, the size of a city, and then you say you're okay. The signal losses are tolerable. But you want to really use it in a practical way over distances of over 100 kilometers, right? It starts to get tricky. And when you start to talk about distances of thousands of kilometers, then that is actually quite impracticable because we simply do not have a quantum repeater. And so the challenge of a small group of the community is to look at the problem of range and how to overcome that. And to do that, we rely on satellite techniques. For example, in this slide over here, I show you some of the basic building blocks of how you would actually use satellites to augment ground-based networks for quantum communication. And this is something that would work for quantum communication in general and not just for quantum key distribution. But of course, in my talk, I'll just focus on QKD. So in typical, there are four building blocks. There's the uplink approach where you put your transmitter on the ground and you transmit your quantum signals to a receiver on the satellite. And then there's a downlink approach, which is the reverse. Transmitters in space, it transmits the quantum signals to the receiver on the ground. If you're interested in entanglement distribution, and entanglement, the most basic form of entanglement is where we produce two photons with very strong correlations. And if you produce this in space, and your spacecraft has two telescopes, you can actually transmit these two photons directly down to the ground stations at the same time, allowing these two receivers that are very far apart, that don't have line of sight of each other, right, to actually receive these photons if they survive the transmission process, and allow these two receiving stations to actually pick up entanglement correlations. And if they pick up enough of these correlations, they can do quantum key distribution. Then there's of course ideas on how you can actually secure communication links between satellites using inter-satellite links. Now, if you want to talk about QKD in particular and how you want to augment the ground-based networks, then you'll be interested in options 1, 2, and 3 in general. Now, option 3 is very nice because if you have entanglement and you distribute the photons to the ground, you don't have to trust the satellite, right? But it has some limitations. For example, the losses are double, and also you're restricted to communications where both stations need to see the satellite at the same time. So if you're talking about having a ground receiver in Israel and one in Singapore, right, then I think option number 3 is going to not work because there's no satellite orbit which allows the two stations to see the satellite in a practical way at the same time. So we often think of options 1 and 2, right? And options 1 and 2, these are what we call a single trusted node model, where you can do quantum key distribution between the satellite and the ground link. And as the satellite orbits the Earth, right, it can carry out quantum key distribution with another ground link. And now the satellite will have a common set of secret keys, and it can do an XOR on these keys and then publish the result, such that only the two selected ground links can actually reverse out the secret key. So you can think of this as some kind of embassy model, where if you have embassy sites around the world and you want to have your own satellite to distribute the secret keys, you can do that. Now, so far, these ideas are nice, and they actually stretch back to about, I think, 30, 35 years in the literature where people have started talking about doing this. But we do know today that this is actually a practical technology because our colleagues in China, they have built the Misha spacecraft, which is a 600-kilogram spacecraft that has, a decoy state QKD transmitter. It has an entangled photon phase source. It has 2 optical telescopes, and they've been using Mishas to demonstrate all the basic building blocks of quantum key distribution. So, when I talk about the three configurations in my last slide, 1, 2, and 3, Mishus has actually shown all of these three techniques. They have shown that it is actually possible, right? And they have actually used this satellite to link up ground stations that are about 1,500 kilometers apart in China. Right? So this is actually a technology that has been demonstrated as a proof of concept. And now the challenge would be how does one try and push the technology maturity such that it becomes a little bit more practicable? And this is an area where I've been working on for the last 10 years. And in particular, the approach that my team has taken is that we study these small satellites that are called nanosatellites or CubeSats. And the idea is that can we do some, of the basic configurations of a downlink or an uplink using a nanosatellite. So for example, a nanosatellite would be about a 10 kilogram spacecraft with 6 units of these CubeSats. And can we actually install some fine pointing mechanism with about 3 microradian fine pointing accuracy that can actually beam quantum signals down to a ground station, right? And we've been studying this problem actively with colleagues around the world. One of our earliest papers analyzing such a link was published in this particular journal back in 2017. And in the meantime, what my research team has been working on is building small entangled photon systems that can be actually fitted onto nanosatellites. So, in other talks, I have spoken about how we've done that. We actually have a CubeSat at the moment called Spooky-1, which is actually the satellite you saw in my first slide coming out of the space station, which is demonstrating the operation of an entangled photon space in source as we speak. Spooky-1 is actually quite successful. It has been in space for over 2 years now, and is continuing to produce entangled photons. Now, what we are lacking on Spooky-1 is we don't have the transmitters and the fine pointing mechanism. What we're doing in Spooky-1 is testing the entanglement and making sure that we're producing the photons. Now we know how to do that. We want to see how, in our next missions, we can actually couple these light sources to these fine pointing telescopes. And we've been working with colleagues around the world on how to do that. One of the projects that was just published this year was a collaboration between my group and MIT and the University of Arizona, where we studied what type of optical front end could be installed inside one of these nanosatellites. Now, you're looking at a picture of one of these telescopes. It is a 95 millimeter primary mirror. Okay, at the back over here, we're going to install a fast steering mirror, which we can actually purchase off the shelf. And if you are interested in the details of this optical front end, you can go to this conference article from SPIE and take a look at it. But essentially, what we did in this paper was we studied what was the size, weight, and power required of such an optical front end. And then we did an estimate of what kinds of downlink quality such a telescope can actually achieve for us. So in this table, right, we talk about a couple of things. For example, if you have such a satellite with such an optical front end, right, what is the wavelengths that you need to think of? What is the fine pointing accuracy that you need? What's the transmitter divergence that's going to happen? And so I want you to pay attention to the last column in particular, okay? So the quantum signals that we are going to transmit from this nanosatellite will be in the near infrared. We can tune our source to transmit photons from either 760 nanometers to 790 nanometers. We believe that the source, intrinsically can produce 25 million photon pairs a second, right? This is at the source. Now, it's often very, tempting for someone new to the field to think that, you have losses, right, between the satellite and the ground station. So you can just, increase the brightness of your source by turning up the pump power. Now, that works for classical techniques, but it doesn't quite work for a quantum signal, like how we're producing entangled photons. And this is because it is a nonlinear optical process and is governed by Poissonian statistics. So if you were to turn up the pump power too much and perhaps decide you want to produce 100 million entangled photon pairs a second, what's going to happen is that when you start to compare the time tags that occur at the detectors, right, the likelihood of multiple pair events that's happening would actually be quite high, and this can actually contribute to your error rate. So one has to study the downlink properties and then try and tailor the appropriate brightness to improve the transmission properties of your link, okay? And the other thing is you have to take care of turbulence. You need to actually model the atmospheric effects. And in Singapore, we actually think that we have one of the most challenging effects because unlike the MISHA's demonstrations where the ground receivers were in high altitude environments, we are trying to put a ground receiver at sea level, right, in a tropical environment with high humidity. So one has to model all of these things together. And when you do that, you can actually begin to also take into account some of the quantum properties, okay? For example, one thing that we often worry about is the quantum bit error rate. And one way to think about quantum bit error rate is what's the intrinsic quality of the entanglement that you're producing at your source, okay? Then technically you worry about noise in the detectors. It turns out that if your detectors are in space, right? Because we're producing entangled photons, half of those photons, is kept in space, we time tag them, and the twins are then transmitted down to Earth, and then we time tag them as well. And it turns out that noise on the detectors in space is not so much of a problem. It is the noise on the detectors on the ground, which is at the far end of a very lossy link, which is the problem. Because if the detectors at the far end start to get really noisy, you begin to see a lot of accidental correlations, and this contributes to your observed error rate as well. So all of these things need to be taken into account. And we believe that there are some numbers here. For example, we believe that on the ground, we should be able to get each detector to have intrinsic dark counts or below 1,000 events a second. And we can also limit the background light to about 1,000 events a second per detector. And this works in our favor because although we are in an urban environment with lots of city lights, one can actually do filtering because a lot of the light that humans use is actually not in the near infrared regime. So this is actually something that is very helpful. And of course, one has to think a little bit about how to correct for polarization rotation, because as a satellite flies over the ground station at an altitude of 500 kilometers, the effective polarization state or axis between the ground receiver and the satellite will rotate. So one has to also keep an ability to correct for that. But when we put everything together, one of the nice things we observe is that the total quantum bit error rate we observe is about 5% on average, which is actually something that we can deal with with error correction. So when we put everything together, we saw those results. We actually built a mock-up in the lab where we have a prototypical source, and then we insert losses in one arm to see what happens. So first of all, you see that as you increase the losses, the photons that are remaining on the satellite, they do not change in the brightness, but the twins that are being transmitted are being received at a much lower rate. So the relative efficiency starts to drop dramatically. And when we did the study, we did all the way to a loss of minus 40 dB. And you can see over here how the quantum signals or correlations between the lossy receiver and the satellite receiver are comparing. But the nice thing is, even at minus 40 dB, we are able to produce, about several hundred, bits per second of correlations, right? And if we manage to maintain the quantum bit error rate at about 5% or 6%, we can actually, do error correction and privacy amplification and extract a secret key at a rate of, about 100 events or so a second. And then when you compile all of these events, as the satellite flies over a single ground station for about 5 minutes, and then you add that to, the number of times you can fly over the ground station over a year, you can actually begin to build up a reasonable amount of statistics. So we can actually also include realistic configuration, right? So let's say we study a configuration in Singapore with nighttime operation, with about 170 useful passes a year, right? And if you use the latest results from our theory colleagues about what are finite statistics on QKD that you have to take care of, we find that we can actually produce about 510 kilobits of secret key per year. And this is using a very small satellite and a ground receiver of about 0.5 meter in size. Now, this might seem small, all right? But if you think about it and you dice it up into 256 bits, that's actually quite a bit of, rekeying material that you can actually use. And so, we are now in the next stages of trying to put together funding to launch our next mission so we can actually try and test out some of these models. And so with that, I'd like to end here, and I'd like to thank everyone for your attention.
Thank you, Alex, for your great talk. So we have time for one quick question. So there's a question about the speed of information transmission. The Chinese managed to transmit securely one photo from China to Austria. So can you comment about the speed and what do you think is the extrapolation for the future?
Right. So one has to remember that quantum key distribution is a buffered operation. This means that you carry out QKD, you generate the secret key, you store that in a buffer, and then you run down the buffer as you rekey the material, as you consume that buffer. So I think even fiber-based QKD, we are far away from doing one-time pad type encryption. What we're trying to do is we're trying to solve the problem of the key distribution for symmetric systems that we believe are robust against a quantum computer. And so with the satellite systems, now I can't really comment on this number about 1 bit per second, but what we do is, because it's a buffered operation, we look at the average rate of key generation over a year, right? And I think a properly designed system should be able to generate something that's at least on the order of about 500 kilobits per year.
I see. Thank you. And again, the other questions will be mailed directly to you, so we will answer offline. Thanks a lot, Alex.